Hello everyone, this is Dr. Hopkins recording the next video in our series. And in this video we're going to talk about or explain the third law, the last of the laws of thermodynamics. So here we have the brief descriptions of the third law of thermodynamics. We have one by Nernst, Planck, and then the simple equation. All of them basically are saying that you can't get to absolute zero of 0 Kelvin or 0 temperature. And then Planck goes so far as to define what that means. So if you're 0 temperature, we have no entropy whatsoever. But because we know that it's impossible to remove all of the residual entropy, the degrees of freedom, and so forth, that practically speaking it's unattainable to get to absolute zero. So that's the third law of thermodynamics. So other than setting some kind of cryogenic limits, the one thing we're going to use, or we can use third law for, is we can determine an absolute entropy. Now you'll notice so far in this course we've been dealing with delta, so changes in entropy, changes in enthalpy. Because the third law entropy sets at 0 Kelvin an entropy of 0, we can determine the absolute entropy of a pure substance. This allows us to determine the absolute entropy. So we have our lower limit, 0 Kelvin, and then within a phase we know that entropy changes. We've defined, this is the definition of entropy, and then we put this in terms of in constant pressure, in terms of H and P, which of course we're going to be at constant pressure, so dP goes away, and then we're left with Cp dt over T. So if we want to know the absolute entropy of a system at a particular temperature, all we have to do is integrate from our starting temperature to our final temperature. Or if we're talking about 0 Kelvin to whatever our final temperature is, we integrate this. Now, in this case, we're not just talking about 0 Kelvin, we're not going to have gases. We're typically going to have solids, so we're going to have different phases of matter. So if we're going from, say, 0 to 298 Kelvin, you're going to go through several phase changes. And so the entropy change of a phase change is the enthalpy of that phase change. So say the enthalpy of vaporization or the heat of vaporization divided by the temperature at which that takes place. Okay, so let's take an example, or a general example. I'm not going to do the specifics. So we start at 0 Kelvin. The solid is in some form alpha. Let's say at some temperature, it undergoes a phase transition from this solid phase to this solid phase, beta, right? So it changes the crystalline environment. And then the next will, at some particular temperature, it'll liquefy, right? So it'll melt. And then at the next and then go through that liquid as we raise the temperature until we get to the vaporization point, or the boiling point, and it turns to gas. And at that point, we are in our last phase to whatever temperature we need. So we have our 0 Kelvin at pressure initial, our final, let's just say it's somewhere in the gas. If we wanted to evaluate the third law entropy, we have our initial entropy, which is 0 if it's at 0 Kelvin. And then we have the entropy, so this is from the third law, from 0 to whatever temperature that these two melt. And then we evaluate that interval. These two, not melt, they change from alpha to beta. And so we evaluate that, and this is the heat capacity of alpha. You have the phase change between alpha and beta, so we add that in. And then we go from alpha, beta to our fusion, so that's our liquid, our melting temperature. And in that case, we evaluate it over the heat capacity of beta itself. So the alpha heat capacities, the beta heat capacities will all be different, liquid, and so forth. And so we keep going through this process. We keep iterating all the way up this process until we get a final total entropy. All right. So actually, what do we do at really low temperatures? So actually, starting at 0, you can clearly see, if we're doing a 0 Kelvin, it kind of screws up any calculation. So what do we do at really, really low temperatures, close to 0 Kelvin? And we're not going to derive this. It's derived from statistical thermodynamics, but we're going to do the Debye extrapolation. So at very low temperatures where we're approaching 0 Kelvin, we're just going to use the entropy of that at that temperature is just the heat capacity divided by 3. So the molar heat capacity at the lowest temperature. So if we had some first temperature where we know the heat capacity, let's say 3 Kelvin, and that has a CPM, we just divide that heat capacity by 3. We don't integrate it. And then that would be our first entropy. And then from 3 Kelvin up to whatever next temperature we would evaluate as well. So we would use this for the very low temperature so it doesn't mess up our integrals. So if we were to evaluate, so this is an example of molecular oxygen. If you were to do a total entropy or a third law entropy plot, and you can see from 0 to whatever temperature, it's a particular phase. We have the various solid phases, and you can see the phase transitions are the vertical ones because the temperature doesn't change during the phase transition, but the entropy does because it's undergoing a change from this state to the next. And it adds it all up as you're going along. So this is in joules per Kelvin mole. That is our units for entropy typically. And as we go up the temperature, we see what kind of molar entropy so we can measure our overall third law entropy. So we'll do some of these in class.